Hello Saintsmen, today we're going to be working on section 3.2 for Algebra 1, which is regarding linear functions. Right after examining what a function is or not, we're going to take a look at some functions here and make a distinction of whether or not they are linear. So let's take a couple coordinate planes, jump right into it. Just draw these two coordinate planes side by side, and it's going to give us an example to compare linear and nonlinear functions. Okay, so I'm going to go ahead and draw two functions in this coordinate plane. Of course, on these, we're going to see arrows at the end, meaning that we will continue infinitely in each of those directions. So to the best of our ability, how these things appear linear, it's pretty simple in terms of that word linear. The first part of it is line. We're looking to see whether or not the function represents a line. And if it does, continuously, with those arrows on both ends, then that would make it linear. The function on the left, it curves, so it is not linear. Versus the function on the right is a straight line, so this guy is linear. The interesting thing, though, is aside from seeing the picture, is taking a look here, and we're going to look at this table horizontally. I'm not a big fan of horizontal tables with regard to ordered pairs or order to show a relation. But in this case, they're very useful. So let's go ahead. This is kind of the exception for me when I like these. So 2, 4, 6, and 8. For our x's and our y will be 9, 18, 27, and 36. Now, first of all, we can very clearly see that this is a function because we have unique outputs for every single one of our inputs, right? So for every input, in other words, we are not we have unique inputs for every single one of our outputs. So we're not going to, duplicate ourselves. We won't have, for example, x being 2, it's not going to go to the same number twice. We have a constant increase is what we're looking for. If there's a constant increase in both x and y, that will mean that we have it being linear, not a constant multiplier, but constant increase. This is what I mean. So for example, in our x's, it's plus 2, plus 2, plus 2. This is the pattern that we're seeing. Versus in our outputs, we have plus 9, plus 9, plus 9, right? So between each of those, there is a constant increase. When that is the case for both x and y, that means that this is linear. Okay? That's linear. As long as x is increasing constantly by a number, typically when we'll see these in tables as it increases by 1, but in this case it increases by 2. Then the y, as long as that has a constant increase as well, we're set. Now let's take another look at another relation here. In this one, 1, 3, 5, 7, 1, 27, 125, and 343 are going to be our outputs. And you can already see up here in the x's, for that domain, we have constant increases. But check this out. Plus 26, right? The difference between 1 and 27. The difference between 125 and 127, 125 and 27 is 98. Or the difference between 343 and 125 is 218. This is not constant. All right? Right here, that's what's happening. We're adding different things. Okay? This is non-linear, which is the same thing as not linear. Okay? The term non-linear is the same as it not making a line. Right. Next. Let's take a look at some functions in function form. So here we go. We're going to distinguish which of these is going to be linear or not. So we have y is equal to 2 to the x power. Y is equal to 5x. We have y is equal to 3 minus, not 3, sorry, 2x squared. And then we're going to have x minus y is equal to 12. And then we're going to have y is equal to the square root of x, or rad x, plus 3. The positive 3 is on the outside of the radicand. We need to be able to write in the function form of y is equal to mx plus b, okay? This m is a multiplier. It can be any coefficient. It has to be a real number. As long as that's the case, we're set. This first guy is nonlinear. Why? It's not in this form, right? It's 2 to the x power, not 2 times x. But however, check this guy out, right? That 5 right there, this guy is linear. Why? Because it's the same thing as the m in the other case. Now, plus b, it's plus 0. We're adding nothing to it. So here, that guy winds up being linear. However, let's take a look at this. 3x squared, right? We're doing something funny to x, meaning that we're adding an exponent to it. If it has an exponent being taken to an exponent, or if it is an exponent, that is nonlinear. Now this guy, next. This guy is for sure linear. Watch this. And it's because we can write it in that form. We have x minus y is equal to 12. If we subtract x, right, then you get y by itself. And if we can do that, right, then of course divide by -1 on both sides. Y is equal to x minus 12. This right here is in that form that's over here. Y is equal to mx plus b. M is 1, b is -12. This is linear. However, this last one right here, this guy, it's nonlinear, and it has to do with this. We're taking the square root of x. We're not multiplying anything times x. It's that there's a separate function happening to it. It's a separate operation. So this would be nonlinear. All right. Let's now make a distinction between discrete versus continuous functions. So let's go ahead and take a look here on a number line, because I think this is a good way to see whether or not something is discrete versus continuous. So we can get a really direct comparison, and it's very similar to what we were doing in the last chapter. Now remember, if we can do a few things here. One, I could actually plot individual points. Like I could put a plot at 1, 2, 3, 4, and 5. It means I'm making a separate distinction for every single one of those values. Because those are all being made, not including anything in between them, this guy winds up being discrete. Versus, if it were continuous, it's the case that if we have 1 and 5, including them, but in between, remember we would shade on the line, it means it includes all those numbers in between, not just 1, but 1.1, or 1.5, or 1 3/4, or 1.9999999, right? So all of those are included in between, all the way up to 5. There's an infinite number of numbers in between 1 and 5, versus when it's a discrete function, we have a finite number. Okay? This is finite. This guy has an infinite number. Because it's all that stuff that's in between. All right, next. The linear function, let's do a little word problem. Linear function y is equal to 1.25x represents the cost, which is y, of bottles, which bottles is represented by x, of orange juice. Each customer can buy a maximum of 5 bottles. We're going to find the domain of this function, and we're going to see if this is discrete or continuous. Now we have to consider the realistic nature of the context of this problem. What's our possible domain? In other words, what are the possibilities for which variable? But x. Because remember, domain means x, which means input. What can I possibly put in there? You cannot buy, it is not permissible to buy partial bottles of orange juice. You cannot go to Vaughn's and buy half a bottle of orange juice. I mean, you can drink half and try to check out. They're going to charge you for the whole bottle, okay? Now, you don't have to buy any orange juice, right? So it could potentially be 0 bottles, or 1, or 2, or 3, or 4, or 5. These have to be whole numbers of bottles of orange juice. So there's your domain. However, we got to figure out, is this going to be discrete, or is it going to be continuous? And the reason it's going to be discrete is because we have whole values are required. Again, we can't buy partial orange juice bottles. It's kind of weird. Okay. We could graph it. Why not? Let's do it. I only need the first quadrant. I'm not going to have negative bottles of orange juice. Right? So if I have 0, my output's 0. If I put in 1, right? It's going to be about a little bit higher than 1. In other words, this is 1 comma 1.25. You put in 1, multiply by 1.25. Okay? I'm at 2. I'm going to have to go up 1, 2, and a half, right? So 2 comma 2.5. 3. And it's going to be 3, 1, 2, 3. Almost 4, but not quite, because 3 times 1.25 is going to be 3.75. And we have 4 bottles. 1, 2, 3, 4, 5, right? Because 4 times 1.25 is 5. And last but not least, right? Count up to just over 6, between 6 and 7, because 5 times 1.25 is 6.25, right? And again, if you're wondering how I'm getting these, right, I'm just taking that and inputting right there for y. Is this linear? But of course, imagine if you drew a line right in through those points. It's going to create a straight line. One more example. A runner's speed is 5 miles per hour. The number m of miles, it's a function of number of h hours spent running. First of all, is this linear? Second, what's the domain? And is it discrete or continuous? And then third, we're going to graph the function. Is it linear? Well, reading this, it's 5 miles per hour. There's a constant increase, right? Per 1 hour, it's 5 miles. 2 hours, it's 10, right? And so there's that multiplier. Plus 5, plus 5, plus 5, right? Because adding a constant term is going to ultimately mean multiplication. So yes, this is linear. There's a constant increase. And in this case, there's a constant increase for miles with each hour added. Here's the funny thing. We can add individual miles, or excuse me, add individual hours into this, or it's possible to run for 15 minutes, right? 1/4 of an hour, or run for half an hour, right? Or run for 1 minute, or not even run at all. So the domain in this case, if we don't run, it would be 0. The time can be any number that's greater than or equal to, right? It's at least 0. Meaning, it's going to be continuous. Because there's an infinite number of, there's an infinite amount of time that, right, that we could consider. Now, is time, ending, or is a person realistically never going to stop running? That's not really what's being asked here, right? Even if there were a cap, there's an infinite amount of scenarios that we could consider after 0 minutes. Even if we capped it at 3 hours, we can take fractions of seconds infinitely. So let's graph it again. So H is our domain. It's our independent variable. Miles depends on how many hours we run, so that is our Y, our range. So here's 0, right? And for 1, it would be 1, 2, 3, 4, 5. Here's the best part. These are the only 2 points I need because it's only going to continue in that pattern as long as I put that arrow through that line, showing that it will continue on infinitely. However, stopping at 0. So that's all we have for today. Good luck. Your assignment is on campus.